Welcome to this presentation on fault tree analysis. As I said, my name is Jon Keswick. I founded the business eFunctionalSafety, and fault tree analysis is part of the consulting services that we offer. And in doing that, we also build some online training courses. We're partway through developing a fault tree analysis course. Many companies will be already familiar with using risk assessment techniques such as layer of protection or layers of protection analysis, LOPA. LOPA is, as the slide suggests here, suitable for scenarios where the independent protection layers are clearly independent of each other and of the initiating event. When that is the case, then LOPA is a simpler technique to apply than fault tree analysis. So it works well for many cases, not forgetting, of course, whether it's LOPA or fault trees that you use. When you start to quantify these things, we mustn't forget that they are risk assessment techniques that estimate risk. Just because they use numbers or eventually use numbers, that doesn't mean to say they're necessarily accurate. As it says there, LOPA works well when you have cases where there's no dependencies. But when it becomes problematic to use LOPA is when you have dependencies between systems. So it's a commonplace thing, clearly in the process sector, to separate out the protection layers such that they don't have dependencies. But oftentimes there's cases where there's a mixture of a process control layer and a safety instrumented system layer having some common equipment. Now, of course, if you're still at the design stage, you can choose to redesign so that they don't have common equipment. But that's not always an option, especially if you're in a plant that's already running without doing any modifications. So you can use the fault tree technique when you have more complex structures, as it suggests here on the slide, for cascading events or complex or even sequenced events, although albeit sequence events is quite complicated. We won't be covering that today, but it excels at modeling systems where there's shared elements, where there's dependent failure modes. So failure modes are not truly independent of each other. And ultimately, it provides more precision. Whereas if in a LOPA, for instance, if you say, okay, these events aren't truly independent, we won't take any credit for a protection layer because it has some dependency with another one. The difference between LOPA and fault tree is that in fault tree, you can model the dependency. You can show the dependency within the tree structure. And that means you should get a more accurate or a more precise result. There's some symbology in fault trees to understand. So I'm diving straight in here because I'm assuming everybody knows to some extent what fault trees get used for. We can pretty much model any kind of system. We're going to look at a process example shortly. Now, all fault trees start with what we call a top event. So the top event here is an event that we're looking to try and model. We'd usually have that as some kind of either some hazard or consequence that we're trying to avoid, or we could be modeling a safety function, a SIF. Usually we would use simpler methods to model SIFs, but sometimes if you want to model a SIF in a tree structure with other things, with other events going on, then you may need to model a SIF within the fault tree itself. We usually start with a process of some sort. We'll look at an example in a moment. Focus on the symbols for now. So the first symbol is really the rectangle, which is some kind of event. In this case, the top one is the top event. These rectangles here are intermediate events. And you can see between the events, here's an OR symbol in two places there on the fault tree. What the OR symbol means is very straightforwardly. In the top case there, either the event on the left or the event on the right have to be true for the top event to be true. And in the case of an AND gate, basically event 2 and 3 must be true for the event above it to be true. So we tend to focus mostly on those AND and OR gate symbols. There are other symbols. There are things like inhibit gates and NOR gates. We're not going to get into those in this presentation. And in fact, most fault trees I've ever been involved with don't have to use those other kinds of gates, which tend to get much more complicated to understand. So usually we can do most of the modeling we need with the events and with an AND and OR gates. However, there are a couple of other types of event at the bottom of the tree. We work this way to build the tree. So we work from the top downwards. And then the software, in this case, this is a picture from a piece of software. The software will usually solve the fault tree from the bottom upwards. To do that, it needs these basic events to have some probability or frequency associated with them. Now, we'll get into quantification in a moment. Let me remember to focus on the symbols. So a basic event will be an event like a failure of a piece of equipment, and we can assign that a probability of failure. It could be a probability of failure on demand, or it could be a failure frequency. We'll see an example shortly. The basic events get probabilities or frequencies assigned to them, and then the tree structure will take those probabilities upwards in the tree to solve what the probability or frequency of the intermediate and top events are. So basic events, the ones with the circle here, you'll see are things that we would always see in a fault tree. There are other types of event which you may see but are not that common. There's a thing called a house event, looks a bit like a house. That's an event that you can either say is always false or is always true. False wouldn't have much impact typically, but if you say that event is always true, then that's a way to represent that in a fault tree. Another one is the diamond symbol, where you've essentially got an undeveloped event. So if we want to assign a probability to some kind of event without actually having to model it, an example might be some kind of external or weather related event, which you're not going to go and look at all the possibilities. It might be windy or sunny on a particular day of the week, but you might want to assign a frequency to that occurrence. Then you just say that's a frequency that's not developed, but we're going to account for it in the tree. Then there's one more symbol. You'll notice here this triangle symbol, which is a transfer symbol. This one's a transfer in. You can get transfer outs as well. In this particular piece of software, it's a way of representing different pages in the fault tree. So rather than trying to build a tree and then understand it from top to bottom on a single page, you can put fault trees over multiple pages and have events transferred in from other pages in the tree structure. So that's the symbols. Just a quick recap, the majority of the symbols we see are OR gates. So any of the events below an OR gate, and OR gates can have more than 2 entries, as you see here. What that means is every single one of these is possible. If any one of those occurs, the event above it will occur. Whereas in this case, it's an AND. Again, ANDs can have more than 2 inputs as well. So here's an example where the top event is a high temperature in a reactor, and it's given a label. You can see the label there is TE1. It could be labeled anything. But the fault tree labels in a piece of software like Isograph have to be unique. The descriptions can be any text you like, but the symbols have to be unique, and there's a reason for that, which I'll come back to shortly. So we've labeled this CW for cooling water, reaction for reaction. So there's two possible causes of high temperature in the reactor. One is loss of cooling and the other way is a runaway reaction. And then in each case, there are multiple potential causes of, for instance, loss of cooling. You don't need to know any mathematics to follow the tree structure. So we can see that in this case, loss of cooling can happen because either there's no water supply, there's a blockage, or there's a failure of booster pumps. So all three of those are possible causes of loss of cooling, which in itself is a possible cause of high temperature. The beauty of fault trees is it doesn't require a lot of knowledge to read it. It's more about the interpretation, and building it's a bit more complicated than reading it. Building it, there are various things and rules you have to follow. But qualitatively, so without quantifying this particular example fault tree, we can see the way that faults interact with each other. So we can see, for instance, there is a possibility of blockage, and that's directly itself, without anything else happening, a potential loss of cooling water flow, that is, cooling water flow. The one case where there's an AND gate in this tree structure are the pumps. And we get a failure of cooling water booster pumps only if we get the primary booster pump fails while running. So that'll have a frequency assigned with it. And we get the standby booster fails on demand. So that the concept there would be a standby pump arrangement. And we can include that in the model, and we can look at a frequency of this occurring and a probability of failure of the standby pump occurring. What is it you look for when you look at a fault tree that someone else has developed? Because that's actually a skill in itself. I'll give you an example where I have to do that relatively regularly, is during functional safety assessments. If I'm the assessor looking at a project where somebody else has developed a fault tree, it's clearly important that I can understand and follow the fault tree myself and ask questions if necessary. So I have a checklist which I use to go through these steps, if you like, verify the structure, look at what it's trying to represent in terms of the events on the tree, compare that with the process, then use that to determine whether the failures and the events are propagating correctly through the system. I would also check the AND and OR gates are appropriately applied. Sometimes people just use the wrong gate, and that might be purely a human error, but the software doesn't know. It still requires people to look at them and to say, does it make sense? The second one there, validating completeness. Look for missing failure sources, overlooked dependencies. So we're looking for all credible paths to the top event via intermediate events, and then down to the bottom of the fault tree, looking for both equipment failure and human error. Completeness, of course, is tricky because how can you verify if everything's been included? Check for repeated events. So repeated events can occur when you get fault trees which are much larger. You can have events in multiple places. It doesn't seem to make sense. In a small fault tree, you would see it fairly straight away. But the reason for repeated events being an issue is if you take the same event in two or more places, you'll get optimistic results if they're solved through an AND gate. I'll show you an example of that in a moment. It partly depends on whether you're using a modeling software. A modeling software should account for repeated events if it's used properly. There are other checks to do. This is the first set of checks about how the tree is structured, whether it's complete, and whether there's any kind of repeated events. There's nothing quantitative in any of those first three steps. It's purely looking at and comparing the tree structure from a perspective of the actual process. If you quantify a fault tree, on purpose, I haven't named these events because this is not. This would be even worse if you were using something like solving it by hand, gate by gate, which is doable, but you have to be careful. And really, because of the relative cost of software, if you've got any sort of complex fault tree, you definitely don't want to be doing it by hand. But even if you did it by, I don't know, putting it into an Excel spreadsheet, I have done that in the past. It's again possible, but then you've got to be very careful how you solve the gates. So this particular piece of software manages all that for you. It uses things called minimal cut sets, which I won't talk about now because it's not really the topic to go into depth here in an introduction. The fault tree software, the isograph software, is very good and does look for problems like we're going to discuss here. Firstly, when you're quantifying something, you'll see typically on a fault tree values inside the labeling. When the fault tree had a calculation, the calculation at the top event there is coming from the sources of event below it. So these are the three sources at the bottom. And then there's an intermediate event, which actually in this case is the same frequency as the top event. Sorry, unavailability is the top event. And it's solved from the bottom upwards. Now, in this case, we can see if approximately, if we summed up the numbers, so the Q or the unavailability numbers, you can think of that as probability of failure. So there's no frequency assigned with that. We would go through this on our online course in a lot more depth, but very briefly, a probability is like a percentage, essentially. A probability of failure of 0.1 means it's going to fail 10% of the time. 0.1 plus 0.1 you might think is 0.2, but actually, from a probability perspective, if they're independent events, it's 0.19. And I'm not going to describe why now, but you'll have to believe me. That's correct. Approximately it's 0.2, but not when you do it accurately. So the 0.19 gets ANDed or multiplied with the 0.1 here to become 0.019. So I know it's not very clear necessarily on your screen, but that top number says 0.019. So the tree is solved correctly based upon that information. The two items I've highlighted in yellow and green here are important just because when we look at the next tree, it'll look very similar. In fact, it's the same except one minor difference. So that result, 0.019, remember that, that's quite a small number. Now, if I quantify that tree again, except I've coloured these two red, really just to show that they are the same event. So instead of on the previous one, just go back. On the previous one, event 5 and event 7 were different events. On this one, event 2, you'll notice the label's the same for both of those events because they're the same event. I saw this recently on a functional safety assessment I was leading. They labeled these events differently here. So event 5 and 7 were looked at by the software as completely separate events, when in actual fact, the descriptions inside suggested they were the same event. So they had come up with an answer, a solution equivalent to 0.019 incorrectly, because actually when you've got the same event here and here, taking them through an AND gate because they get solved through this direction, taking them through an AND gate does not give you event 1 multiplied by itself. It gives you the same probability in this case, or unavailability, it gives you the same result. So 0.1. So in this case, the modeler had incorrectly used two different events but described them the same, and they were the same event coming through the tree in different places, and that had a big impact on the result above. So that's just an example of repeated events and how things could go wrong. A third example here just shows you that it doesn't have to be unavailability you're modeling. In this case, the high reactor temperature that we saw in the earlier example has now got some frequencies associated with it. Anything with IEF is a frequency, so the W parameter, and anything with a PFD is a probability of failure on demand or an unavailability number. In this case, what the tree will do is it will model for the failure frequency, because actually although this unavailability issue is present here, from a frequency perspective, it doesn't impact that W result. So we're either using a fault tree to model for unavailability, or we're using it to model for frequency. And quite often we're looking at modeling frequency to try and compare that with a target frequency of an event to make sure that we don't go over a certain frequency. I'm not going to try and show you a live tool, although if you come on our self-paced course, we will be showing examples of live building a fault tree, how to build it inside the tool and how to enter the data. There's a couple of other things to be aware of in fault trees. When you're quantifying them, you need to have quality data. So the garbage in, garbage out principle applies like all reliability modeling methods. And you want to make sure that data is both entered correctly. You've got all types of failure models, failure rates, test intervals, detected and undetected failures, etc. So there's a lot of information to model, and it's really easy to muck that up in a fault tree software. If you were just going to do something like a calculation for a safety function, like the example on the right here, to calculate the probability of failure of a SIF, I would typically tell you not to use a fault tree. Use a reliable tool like the AE Shield tool, which is very good for modeling straightforward structures, including relatively complex voting as well. And you can enter the data much easier into a tool like that than you can into a fault tree. So it's horses for courses. I wouldn't suggest you use a fault tree for just doing regular SIL calculations, unless you've got something particularly strange or complex, or something with dependencies between systems. And I know my face is covering the part of the text here, and I apologise for that. Check for common cause is what it says. So there's an example here on the screen of two sensors, and you'll see there's a very small symbol next to them called a beta symbol. And that just tells me that behind that common cause factor that's been applied, so that although that's a redundant sensor from a point of view of a 1 out of 2 arrangement, from a safety perspective, the common cause would have to be included. So I can see that common cause symbol on the diagram, and then I'd have to go and check the data tables to make sure that there's an appropriate factor been applied. So there's issues around quality of data, there's issues around entry of data, and you will get bad results if you use bad data. Just before I open up for questions, I wanted to give you an example of what's coming with this self-paced online course. So you've just seen a little bit of the introduction. What we're planning to go into is probability of frequency, give you all the background, about understanding the probability and frequency numbers, because if you don't have that, then you can't really develop a fault tree or use a software very well. Because we've had significant experience of using the isograph software, we're going to build that software into our online course. It would be better, of course, if you had that type of software available to follow along, but you'll be able to see exactly how we would set up the software, because there's many parameters inside these softwares, and they're not, this particular one gets used across different sectors. So it gets used in aerospace, in rail, in all sorts of different industries. So it's not designed specifically for process applications, which means you have to configure it properly. The text there says example process and fault tree analysis building on FTA structure in the software. So we'll go through worked examples. Rather than the examples I just showed you in a slide there, we'll actually build them on the screen in a video in this online course. And then in addition to that, quantification. So how to, once you understand all the failure data and how it works, entering data in, frequencies, common cause factor models, using all that, doing all that properly, and then showing the results and how you can do sensitivity analysis. Finally, modeling failure examples. So using the model you built to do what if failures, so you can show what if something fails, how does that propagate within the fault tree and affect the numbers above it, such as redundant elements. So for instance, if you had a 2 out of 3 voting arrangement, you can fail one element and see what impact that has on the probability numbers above it. And then finally, using the fault tree analysis in event trees. So event trees not something I've introduced here because it's just wasn't enough time to do that. Part of our online course, we will link fault trees and event trees together, because event trees are very good for showing multiple different consequence outcomes, and they can be combined very well in a software like Isograph to show you consequences from the top events. So there's a first question here that says, we're using FMEA for machine safety. What I'm struggling with is that dependencies are not clear as fault tree analysis. FMEA becomes a big fat Excel file. Yeah. And reading and understanding is not really easy. The ones not involved in creating in the first place. Yeah. Okay. Yeah, this is about using the correct technique. So I didn't look at FMEA because that's more a technique often used in kind of design of systems. I know it gets used, it does get used as well occasionally in process applications. So you're talking about machine safety. Yeah, dependencies aren't clear in an FMEA. You do get just big tables of data. Fault trees are much easier to follow. And that's ultimately, sadly, just down to the use of the technique. So FMEA will show you certain aspects, but things like dependencies are definitely not going to be clear like they are in fault tree analysis. It's a completely opposite approach, actually. So fault tree analysis is a top-down approach and FMEA is bottom-up. Can you give me an example of an undeveloped event? Is this something we do not know? A new development, we do not have much data. We think new part of the system can fail. So your example or your suggested example, in new development, we don't know. We've got how much data about how something is going to fail. You could use an undeveloped event to at least include it in the system. But my example of an undeveloped event would be, I think I gave the example of a weather being a factor. So let's say you had potential for increase in temperature being caused by a weather system. You can get basic data from the local area that you're dealing with, wherever the plant is located. Obviously, it's never going to be 100% accurate, but you can get an idea of temperature in a certain season. And then you're not going to develop that event in the fault tree. So rather than building all the events below it that might lead to there being high temperature or high ambient temperature, you just say this is an undeveloped event we're going to include for this in the fault tree. we're not going to develop the tree structure to show how it happens. That's my example of an undeveloped event. It could be all sorts of others. I'm looking at the first question. Is unavailability Q in quantified one slide a probability number? Yes, it is. Yeah, Q, I don't know the origin of why Q gets used, but it does. Q gets used in fault trees, at least in the fault tree tool that we use, in the isograph tool, and W gets used for frequency. So the Q number doesn't have any time base associated with it. It's purely a probability number. Do two similar identical devices, both of which have to fail, must always have to include common cause? Yes, they always have to include common cause. You could say the common cause number might be lower if they are non-identical, but even if they're non-identical, there may be some common elements, common causes, but the common cause number would be different. But yes, you always have to include common cause if they're identical devices. You did say identical devices. Yes. So whether it's two valves, two sensors, two redundant I/O cards, it doesn't matter what they are. If they're identical devices and the failure above is with an AND gate, common cause must be accounted for in the tree. And you'll actually find that the common cause dominates the calculation. And without it, it's not a correct fault tree. Just looking across, Svetlana, would you say that fault tree analysis is used for process safety assessment or for machinery operation safety as well? Okay. My personal use of it is mostly has been in process, although I did come across it in a machinery safety application fairly recently in the mining sector. We were not building the fault tree in that case, somebody else was, but they were looking at quite a complex braking system. The best way of showing how the system worked to demonstrate really to the end user that the braking system was adequate. The company doing that demonstration used a fault tree to demonstrate it. And it's the best way, by the way, of communicating. You could also do FMEA, and I think they had done FMEA, but unfortunately FMEA doesn't allow you to communicate that structure anywhere near as well as a fault tree does. So the fault tree really is partly about communication, as in communicating between one company and another about how the system works. And it's partly about then obviously quantification. You could just build a fault tree just to communicate how it works, or how it fails, I should say, to lead to a hazard. Is unavailability Q the same term from the simplified equations from 61508? I don't know, to be honest. I don't know if that uses Q in the 61508. I don't think 61511 has any equations, but 61508 does, part 6 from memory. I've never actually cross-checked what the source is. Does LOPA and FTA give different results for simple, straightforward scenarios? There can be minor differences depending on whatever tool you're using. If the LOPA is built into something like an Excel spreadsheet, if someone has used simplified equations to, for instance, sum up the frequencies, then you'll find some differences. Part of our online course is to show cases of LOPA that can be transferred over to fault tree, and you get the same results. What you might not be able to do is get the same results by transferring fault tree back to LOPA, because by definition, fault trees can model more things like dependencies. So it doesn't usually go the other way. Where do we factor in conditional modifiers in a fault tree? You can factor them in either at the top of the tree. So for instance, the trees we saw earlier, if you're modeling for frequency, then you can factor the things like probability of ignition, etc., at the top of the fault tree. Or lower down in the structure. It really depends on where it's relevant. The other thing you can do is you can take, and we don't have time to do that on this call, but our training course will cover this. You can take the fault tree into an event tree and model all the consequences by applying from the top event, applying the appropriate factors for the conditional modifiers, essentially, that you would often see in a LOPA. You can put those into an event tree. So you take the outcome of the fault tree, and then instead of just applying those modifiers at the top of the tree, you would take that result into an event tree and then show the other factors such as ignition probability. Okay, I think I've covered all the questions. Thank you for attending. I'll come off the screen and say goodbye and speak to you all again soon.